Hello everyone. This talk is based on a joint work with Itai Arath at TechNew in Israel and David Gossett at IQC Canada. Allow me to introduce you to some of the concepts needed in this talk. The central concept will be that of the local Hamiltonian system. This can be viewed as quantum analogs of the constraint satisfaction problems. Quantum complexity theorists care a lot about local Hamiltonian systems since they lead to central problems in quantum complexity theory, somewhat similar to what the importance of 3-SAT, for example, in classical complexity theory. Physicists have been studying these systems for a very long time. In fact, even before condensed matter physics was called condensed matter physics. These systems help model the materials that are of interest in real world. Consider a collection of particles or spins or qubits. And for the purpose of this talk, I will put these spins on a 2D grid. But in fact, one can put these spins on vertices of any hypergraph of one's choice. For this talk, we'll be working with a 2D grid. The system is called local Hamiltonian since each constraint acts on a small number of spins. An example here is that of a placket interaction, which is shown in red. The local interaction H is assumed to be positive semi-definite, which just says that the energy is positive, and we'll assume that the interaction is bounded from above by identity, which in physical terms just means that the energy is bounded for each interaction. Once we collect all these interactions, what we get is the Hamiltonian of the system, which is a sum over all these placket interactions added all of them together. The ground state of this Hamiltonian is denoted by ket omega. It is the eigenstate of the Hamiltonian H with the smallest energy. It's the analog of an assignment that satisfies maximum number of constraints in a constraint satisfaction problem. For this talk, we'll assume that the ground state is unique. The spectral gap is the difference between the smallest and second smallest eigenenergies. We'll consider the case of frustration-free systems, which are the analogs of satisfiable constraint satisfaction instances. Mathematically, it says that each local interaction H views the ground state as its zero energy state. It turns out, this is a technical point, that frustration-freeness allows us to choose each interaction as a projector. This is because one can scale the non-zero energies of the local interaction H to 1, so that I can replace H by the projection of the span of the H. This does not change the ground state, and it changes the gap by a constant which depends on the details of the local interaction, which, by the way, we assume to be a constant. An important concept related to ground states is that of entanglement entropy. To explain this concept, I'll divide the spins into regions A complement, and the boundary will be denoted by partial of A. We can compute the marginal of the ground state on the region A, and we can evaluate its von Neumann entropy. The value of this von Neumann entropy is called the entanglement entropy of the ground state, because it captures the entanglement present in the state. For instance, if the ground state was product across A and A complement, then the entanglement entropy would be 0, which just says that the ground state would be would have no entanglement. The system is said to satisfy an area law for entanglement entropy if the entropy scales as the length of the boundary of the region. The trivial behavior would be that of volume law, in which the entropy scales as the volume of the region, which also happens to be square of the boundary in 2 dimensions due to isoperimetric inequality. Subvolume law sits between the area law and the volume law, and it says that the entropy scales as boundary to the power sum alpha, where alpha lies between 1 and 2, strictly between these. The area law conjecture says that the ground state of a gapped Hamiltonian, in which case the spectral gap is taken to be a constant, satisfies an area law across every bipartition of the region. For most purposes, it suffices to consider regular regions as a rectangle or triangle, or even a vertical bipartition like the one shown here, for the purpose of stating the area law conjecture. Now, what is the importance of area law conjecture? The importance is that most quantum states satisfy the volume law. Thus, if a quantum state, such as the ground state, satisfies an area law or a subvolume law, then it means that it is somehow simpler than most quantum states, and possibly it can be studied in a feasible manner. In one dimension, this has been very well understood. In the breakthrough work, Hastings proved an upper bound on the entanglement entropy for every gapped 1D system. His upper bound was exponential in 1 over the gap. Soon afterwards, Aharonov, Arad, Landau, and Vazirani, they proved the same result using different techniques for the frustration-free systems. This result was exponentially improved by Arad, Landau, and Vazirani in 2012 to 1 over gap to the power 3, and later Arad, Kitaev, Landau, Vazirani, they proved a 1 over gap upper bound for every system, not just frustration-free. These results have very powerful implication both for physics and quantum complexity theory. And it says, these results say that gapped ground states can be represented by a small number of parameters, which is interesting for quantum complexity theory purpose. And it also says that the physical properties of the ground states can be computed efficiently using this representation, which is very important for physics. In 2 dimensions, a series of prior works are known, and area law has been shown under several assumptions. One assumption is that there are a small number of low energy eigenstates. Another one is that we are working with spin half particles or qubits with nearest neighbor interaction. There is an adiabatic assumption, and there is an assumption on specific heat. A priori, it's not clear what these assumptions have in connection to the area law conjecture that was stated earlier, because they may not relate to a constant spectral gap. It's important for this talk, the following point, that for the commuting case, that is the commuting frustration-free case, for any commuting Hamiltonian, which means that H and H, the neighboring H, they commute, area law holds in all dimensions. Now we'll discuss some techniques that are known for upper bounding the entanglement entropy. Let us recall the bipartition that I showed you earlier. The idea for proving an upper bound on the entanglement entropy is to approximate the ground state by an operator K, which has some nice properties. To describe these properties, let me define the Schmidt rank of the operator K across this bipartition A complement. The Schmidt rank is the smallest value D, such that K can be written as a sum of product operators, where the sum involves only D such product operators. A series of the series of works mentioned earlier, that are Hastings, Aharonov, Arad, Landau, Vazirani, and Arad, Landau, Vazirani, they developed a scheme to define and use these operators in proving the result. The requirement was to find an operator K which is close enough to the ground state, and its Schmidt rank is as small as possible. And under good trade-off between these 2 parameters, one can prove a nice bound on the entanglement entropy. I will not go into the details of these properties of the operator K. Rather, I'll carry forward with an important insight from the works Arad, Landau, Vazirani, and Arad, Kitaev, Landau, Vazirani, which was to view K as a polynomial of the Hamiltonian. To understand this point, let us view ground state as a function of the Hamiltonian. Let me define the function f ground, which takes a value 1 when the parameter x is 0 and it's 0 otherwise. Notice that if I feed the Hamiltonian into this function, I get the ground state. Now I can approximate the function f using polynomials, which are well studied in approximation theory. And the upshot is that low degree polynomials lead to low Schmidt rank, which is what we desire. So here again, here's the function f ground, and it is shown in the figure here as a blue line, and it's 0 everywhere else. Our goal is to find a polynomial, which is the green line, which well matches to the function value at point 0, and it stays as small as possible because it has to approximate the ground state for the function f ground. So it stays as small as possible in the range in the range of eigenvalues of the Hamiltonian, which is from the gap gamma all the way to the norm of the h. We don't care what happens in the region which is not part of the eigenspectrum of the Hamiltonian. Also, we don't care anything that's beyond the largest eigenvalue of the Hamiltonian. What is well known is that the Chebyshev polynomials for a fixed degree achieve the smallest possible approximation of this kind. This is precisely what was used by the prior works that I mentioned earlier. Now the Chebyshev polynomials achieve an approximation error of 1/3 with a degree square root of the norm of the Hamiltonian, roughly. And this fact works very well in one dimension. And it gives us the very good dependence on the gap that is 1 over the gap for the 1D area law. But unfortunately, this polynomial still gives the trivial volume law in 2 or higher dimensions. But recall from a previous slide that in the commuting case, the area law is already known. Then we can ask that why does this approach of using Chebyshev polynomial does not really give area law for the commuting case, while the area law is already known. And we would like to understand and recover the area law for the commuting case. For this, our starting point is an improvement to the Chebyshev approximation, which would be more suited for the commuting case. And it comes from the work of Kahn, Lineal, and Samarodinsky. They constructed a polynomial, which I will call the KLS polynomial, which was meant to approximate the AND function of n variables, where each xi is a bit, by a polynomial of this quantity, which can be viewed as a Hamiltonian of certain sort. And this is well suited for commuting case simply because the commuting frustration-free Hamiltonians have integer spectrum, for instance, the way it's shown in the figure. Now, this directly relates to the fact that this quantity takes integer fractions, that is 1 over n or 2 over n all the way to n over n. Now I can use this approximation to f ground, which is the same as the approximation that was constructed here, which only for the integer spectrum. And what one obtains from this work is that an error of e to the power minus degree square over the norm is possible for all the degree in the range root of the Hamiltonian to the Hamiltonian's norm. This is better than the Chebyshev approximation. If you take the power of Chebyshev approximation, you will get something bigger than this, whereas this gives a quadratically better approximation error. And if you use this approximation, then you find that the area law for the commuting Hamiltonians can be recovered, unlike what happened in the Chebyshev approximation case. So can we use this polynomial to get an improved result for the non-commuting case? Unfortunately, we cannot, because the construction of KLS polynomial heavily uses the integer spectrum, and the non-commuting Hamiltonian has a continuous spectrum. This, given this, we'll now go to our techniques in the result. Our approach will be to try to recover the KLS polynomial behavior using a different and a quantum-friendly construction. We'll use this construction. First, we'll do it for the case of approximating AND function. We'll use this. We'll try to fight the non-commutativity issue, and we'll try to get an improved approximation for the ground state in 2 dimensions. We'll be requiring a local gap assumption for this, which states that the Hamiltonian restricted to certain subsets that I'll show later is also gapped. An important tool for our construction will be that of the robust polynomials of Scherstoff. So fix a Boolean function p, which takes m bits and outputs a bit. and let's say its degree is d. Shortstop showed in 2012, in stock 2012, that there is a polynomial, let me call it ROB of t, which takes m real values and it outputs a real number. The degree of this polynomial is at most twice the degree of the Boolean function t, and it is robust. What it means is that if I take any binary string x1 to xn and I corrupt the values of x1 to xn by any error e1 all the way to en, where each ei is a small perturbation between a constant perturbation between -1 over 10 to 1 over 10, for instance, I feed this corrupted string to robust polynomial, and it turns out that the robust polynomial stays very close to the original value of the Boolean function, up to an error plus minus 2 to the power minus d. An important point to notice here is that higher the degree under consideration, the approximation gets better. So let's use a robust polynomial to get an improved approximation for AND along the lines of the KLS polynomial, but this is a different construction. Let me arrange the n variables in a manner similar to the two-dimensional Hamiltonian that I showed earlier. This arrangement is not necessary, of course, for the case of classical variables, but it will help us to connect to the construction that I'll show later. I'll divide these n variables into t groups, these t big rectangular groups, and I'll write the AND function on these n variables as a composition of AND on the t variables followed by evaluation of AND inside each block. The construction is as follows. We'll approximate the AND of n over t by a Chebyshev polynomial q with error 1 over 10, which is what was allowed by the Shortstop construction. And the degree will be approximately root over n over t, which is what Chebyshev polynomial achieves for constant error. Next, I will take this polynomial q, which approximates AND, and I'll feed this into the robust version of AND t. This using this error guarantee, I'll get an error guarantee here too. And if I just compute the degree versus error trade-off, it's seen that the behavior of the KLS polynomial is precisely recovered. Now let's try to run the same analysis in the 2D setting. Now we're back to the 2D Hamiltonian system that I discussed earlier. Let's, as before, as in the previous slide, let's divide the Hamiltonians into blue blocks. Note that we're missing out some Hamiltonians here, which will matter very soon. And let's assume that the Hamiltonian in the blue blocks is gapped by the local gap assumption. The first step, that was to approximate the ground space of each block by Chebyshev polynomial q with error 1 over 10 and degree roughly root over the, sorry, this is not the norm, this is the norm within this region over t. Sorry, this is the actual norm. So this step is, as before, due to the local gap assumption, I can always approximate the ground space in each block by this polynomial q. And I will also do the robust polynomial construction step. This also turns out to be quantum friendly. But what happens is that we only get the ground space in these blue regions, and this step is missing out a large fraction of local Hamiltonian terms. All these red interactions on the boundary are not satisfied. So we haven't proven anything for the ground state of the Hamiltonian. To get around this issue that this construction does not give us the approximation to the ground space of the full Hamiltonian, rather only to the Hamiltonian on the blue region, we'll use the coarse grain directivity lemma, which was shown in some prior works. The lemma says that if instead of taking the product or the AND of these blue projectors, I take the blue and the overlapping set of red projectors that are shown in the background. And let's say the overlap between the red and the blue projectors everywhere is at least m for the neighboring projectors. Then it turns out that the product is exponentially close to the ground space, where the m parameter corresponds to this length scale. Now I can use this lemma, the coarse grain directivity lemma. I can combine with the construction that I showed you earlier. And if I repeat the analysis The same analysis as before for the KLS approximation or the improved approximation to AND. But I also include the additional error due to the Directivity lemma, the coarse grained Directivity lemma. Then I arrive at the main theorem, which is that the locally gapped frustration-free systems, assuming the local gap is a constant, satisfies a subvolume law with a subvolume parameter 5/3, which is less than 2 and still greater than 1. Now let's discuss some future directions and open questions. Recall that a general Hamiltonian H has continuous spectrum in the range gap to the normal Hamiltonian. This is true even under the local gap assumption that we assumed for this talk. Thus, a polynomial of the Hamiltonian itself cannot improve upon the Chebyshev approximation, which is known to be optimal for this kind of approximation. But what we have shown is that under the local gap assumption, if we use the local structure of the Hamiltonian, then we can go beyond this Chebyshev approximation and we use the Shostov's robust polynomial for this purpose. The main open question that we leave unanswered is, can we use the local structure to completely mimic the approximation error of the KLS polynomial, even in the non-commuting case? There are several other problems that we leave open. So another important problem is to remove the local gap assumption that we made earlier. It would be great to generalize this, generalize the subvolume law to the frustrated case, which we believe also is connected to the local gap assumption. That means answering this step might lead to an answer to this step. A recent work of Abrahamson this year shows, using our construction and the prior works on polynomial time algorithms to quantum ground states, that a sub-exponential algorithm can be obtained for preparing locally gapped precision-free ground states. And an interesting question is whether this can be improved using the two-dimensional structure. Finally, there are several information theoretic limitations on the utility of area law for efficient representation of ground states. And an interesting question is whether construction of our AGSPs could be used to circumvent these limitations. Thank you for your attention.